So maybe the back you may not be able to hear. So if you can, then tell me. I will try to scream a little bit louder. Okay, so yes, I have been working in different fields. Initially, my career started in condensed matter physics. Then I moved to atomic physics, plasma physics, and eventually ventured into astrophysics and cosmology. So today's topic is the universe 26.7 billion years old with no dark matter or dark energy. Age is you can measure my age. I was born on that day, and this is the age. But in the universe, you don't know the age directly. It depends on the model. You can measure. You make certain measurements, just like I will say what the redshift is. How many people know what the redshift is? Oh yeah. Okay, so I'll have to explain a little bit about the redshift. Okay, but this is what you measure is the redshift, which I will explain in a moment. And you measure, when you say this is the size of an object, you don't measure a physical size. You measure their angular size. Same as about the sun or moon or something. What do you measure? You measure their angular size, and since you know the distance, you can decipher what their physical size is. Okay, so this is what we have to keep in mind. Age is not written that in just like our age or age of any other thing which we know is born and then finished at a certain period of time. So keep that in mind. So let's get going with that one. Let's see. What happens is the James Webb Space Telescope was launched on Christmas Day in 2021. It had an unexpected observations in the summer, starting in summer of 2022. Some of the unexpected observations which are of interest to me and we will discuss today are this: excessively large number of galaxies in the very early universe. A universe was only about 2% of its age according to standard model, or 3% of its age, that is about 3 to 0.5 billion years old, whereas its age according to standard model is 13.8 billion years. This was not foreseen by the standard cosmological model. Galaxies in such early universe have disks and bulges, which indicate that they have passed through a long period of evolution. Just like, if you see somebody, you cannot have somebody who is 3-year-old really, but looks like a teenager. There must be something wrong. Either this person grew very fast, or our estimate, we have our date of birth recorded wrong. Spectroscopically, these galaxies resemble their counterpart in the local universe, and the smaller galaxies appear to be more massive than larger ones, which is quite the opposite of the common view. Some of the early galaxies had this kind of property. Okay, so what is the difference in the two telescopes? This is James Webb telescope on the right side, and the Hubble telescope, which was launched in the 1990s and started giving data, good reliable data in the mid-90s, which is really changed. The Hubble telescope really changed our perspective of the universe at that time. This was one of the most important space launch of that time, which really changed our perspective and gave the strength to standard model, which is called lambda CDM, cold dark matter, plus lambda, which is the dark energy. We will talk about that, which gives the strength to that model. Before that time, people were not certain about the age of the universe. In fact, first when in the 1920s, 28, 29, around that time, when Hubble discovered that the universe is expanding. At that time, they estimated the age of the universe to be about only 2 billion years. And before the launch of this, the astronomers were uncertain. They were thinking age could be anywhere between 10 to 20 billion years. So age is a factor which the age we know and which is accepted today of 13.8 billion years is because of the Hubble Space Telescope, which provided us very good data, high precision data, which was used then to create a model which really gave us the age of the universe to be 13.8 billion years. Now come to next phase of the space launch, which is James Webb Space Telescope. This started giving data in the summer of 2022. As I mentioned, this really provided another perspective, even more sensitive telescope in a range which was not covered by the Hubble telescope, that is the infrared range. In that one, we obtained data, and from that data, it is now somewhat uncertain. This telescope is able to see deeper into the space, James Webb. Hubble was able to see up to about 1 billion years after the Big Bang, according to the standard model. And this James Webb can see up to 300 million years after the. So it can see deeper, so it can see more of what is happening in this region. So this is why it provided a whole lot more information, and then says, does our model, which has been developed to date, the standard model, does it also apply to the earlier time in the same way as we know it applies to the earlier time? So this is one thing we will discuss about that, how it changed our perspective. Now this shows what Hubble had done. Age of the universe, it crystallized at 13.8 billion years. Then it also said at the time, in the early 1990s, it was believed that the universe expansion is slowing down with time. But observation was that it came out from this telescope that really it was accelerating. What is causing the acceleration? And then they have to invoke the dark energy, or lambda, what is called cosmological constant, which was introduced by Einstein and rejected later on, but it was brought in to explain the accelerated expansion of the universe. So that is what established dark energy. And the model which was developed, it gave the matter density to be more than what we can observe in the universe the way we know, like something made, we can see around, a chair made, ourselves made, and everything. It is much more. It was 5 times, 6 times more of the unknown matter than the known matter. So what is that matter? That's why we gave the name of that matter to be dark matter, and people started looking as a particle in a large hadron collider or colliding machine which people use to find new matter. They start looking for that, and that's where dark matter also came into existence, although it has not been directly observed to date. Then also it says what planets form, what the black hole is at the core of all the galaxies. That also came out from Hubble. Now James Webb, we are able to see deeper, and it is questioning some of the things which Hubble had found, or the models which were developed based on the Hubble observations. So what it says, what is the age of the universe? Why? We will discuss about that. Galaxies in very young universe exist at less than 0.5 billion old universe. They are highly evolved. As I say, how can somebody, a teenager like person, be seen at the age of 2.5 years or 3 years old? and they are highly evolved. The dark matter and dark energy, that is, are they real or not? That is again something which is being questioned. There are other satellite, other space and land-based instruments which are also looking for the dark matter and dark energy, whether they are really true or not. Then exoplanets. Does the planets outside the solar system, they exist? And if they exist, are they habitable? Some of the planets are habitable, etc., etc.
So can I ask a question or wait for it?
No, please, do ask.
Okay. The observations made by Hubble, if you look at those observations only, does the James Webb Telescope resolve those observations better?
James Webb, those observations are confirmed by James Webb, but it is able to see beyond that. And some of the uncertainty on those observations which we had, that is what James Webb is trying to find, correct those uncertainties. Yeah. So, for example, Hubble itself had seen some galaxies in the early universe, or we call it cosmic dawn universe, which appears to be impossible galaxy, as if they were very massive and they were very small, something characteristic which we don't expect. But then comes James Webb Telescope, it essentially shows a lot of such galaxies which don't fit the standard model. So spectroscopic observation, they reveal that Mazy galaxy existed only 390 million years after the Big Bang. It is one of the earliest galaxies. And then the glass Z12 galaxy, this is a galaxy of mass about 10 to the power 9, a billion solar masses, which existed only 350 million years after the Big Bang. So how could it form such a massive galaxy in such a short time? But its size, according to the standard model, is only 1 kiloparsec. 1 kiloparsec is like 3.3 light years, 3.3 thousand light years. 1 parsec is 3.3 light years, approximately. Yes.
So actually, when you showed the first video, there was a section called dark age. So all these galaxies are pointing, all these observations are pointing out that there are galaxies on during the dark age.
They could be forming in that time, but forming doesn't. But you can form the galaxy or stars which form the galaxies during that period, but they are not yet having the fusion energy created in that to start shining. So when they start shining, then we can observe them. Otherwise, they are dark.
So James Webb Telescope is also observing these galaxies
After the dark ages, yeah, after the dark ages, yes. But the thing is this: what are the dark ages? When do they start, and when do they stop? That is also model dependent. So if you are able to see in so-called dark stages according to standard model, that means we have something, the dark age not properly defined in that one. That means dark age is further away from us than we thought. Yeah.
Size estimation is very sensitive to the model used.
Sorry?
The size estimate is very sensitive to the model used, because you mentioned two models.
Oh yeah.
Very different.
Oh yeah, of course they are. Of course they are. See, this is why we see, what we see, observe in the sky is certain parameters. Spectroscopically, we can observe the various lines and whether these lines have been moved to the left or right, towards the red or ultraviolet. That's what we observe. Then we observe their angular size or some other parameters. And to decipher age or their distance and everything, these are model dependent. So model are, and if we find that certain parameters of an object don't fit the standard model, then we say there may be something, some limitation of the existing model. That doesn't mean the existing model which we have been using is incorrect. All we know is it has its limitation. It works very well within this domain, but beyond that domain, it perhaps doesn't work. Just like Newton's law of motion. In everyday life, it's great. We can design all the equipment we design, even the launching of a spacecraft could be done mostly by that. But if you consider your GPS system, which you use all the time to guide yourself, if you use Newton's law in there, you will go off the track in no time. That's where you have to bring in general relativity. You don't want to use general relativity when you are driving the car or trying to design a car, how to accelerate or launch certain simple things, a projectile or something, or how to fire a gun. Those things can be done by Newton's law, but not the GPS or something more advanced you cannot do. Or when you are launching a spacecraft in a deep space, you got to make the corrections which are required by general relativity. Even ordinary satellites which we launch, we need to have that kind of correction done. So just keep in mind, then we are not saying that the standard model which is accepted based on Hubble's observation and other observation, Planck observation, we will talk about that briefly also, so many other observations, that there is anything wrong with that. But it has a limitation. So when you apply anything which has certain limitation, beyond its limitation, then we have a problem. Okay, another galaxy which was announced in July 9, 2024, it was in existence 290 million years after the Big Bang, with a mass almost 500 million solar masses. And this one is a big surprise, although not at such a high, so early in the universe. It's 700 mega years after the Big Bang, but it is a disk galaxy, the kind of galaxy we live in, and has the spiral arms and all those, and it has some certain kind of rotation, which we only expect in highly evolved systems. So that's the surprise, that how such highly evolved galaxy could exist in such early universe. Then there was another thing, which is something called little red dots. They possibly are some kind of black holes which are accreting mass at a very high rate, but it is not very clear what they are. Somebody in a recent paper wrote, the physical properties of little red dots currently have order of magnitude uncertainties, because models to explain the continuum of these sources differ immensely. Actually, all these observations were very nicely summarized by Christina in a Quanta magazine, where she gave a title, The Beautiful Confusion of the First Billion Years of the Universe. What she wrote, unexpectedly bright galaxies, mysterious little red dots, surprisingly massive black holes, and galaxies shaped like prickles or bunches of grapes have been spotted all over the young universe. I don't know whether I can use it to, yeah, it has. Okay, that's good. So, what is redshift? Redshift, if you have seen an ambulance passing by you, you find when the ambulance is approaching you, its pitch appears to be higher. And when it is receding, its pitch appears to be lower. So that is what happens, is stretching and compression of the waves, which causes this kind of effect in a very simple way to explain it. So that is for the sound waves. Same kind of thing happens for the light waves that get stretched when the emitting galaxy is receding from us, and these stretched waves being longer, stretching means longer wave, they shift toward the red in the spectrum. And how we define redshift is, I wish I had a better something to, no, but then I will cover the thing. I don't want to cover what I'm, So what is the redshift? This is moving a little bit too fast. Can you slow down the cursor somehow? Can you slow down the cursor, please? It's moving too fast. Yeah, it's better. Let me see. Yeah, this is better. So it's not very good. Anyway. Okay, so what is redshift is defined as essentially the lambda E is the wavelength which is emitted by a galaxy, and lambda O is or 0 is the observed wavelength. So we take the difference of the two and divide by the emission wavelength, and you get some parameter which is called Z. This is the redshift. Redshift is dependent on distance, because farther an object, faster it is accelerating, so more is the redshift. And of course, if it is distance, then distance is related to travel time, or travel time is like all the waves are traveling with the speed of light, so if you know the distance, you know what the travel time, and that way distance can tell. Z can really tell you how far in the past you are looking at the objects. Okay, this one is essentially showing the what was possible to be seen by Hubble Space Telescope, which is shown here. Oh, I hate this. This is not. I usually use a podium to do this, but this is what happened, because the reflecting surface, mouse doesn't move very well on that. Anyway, I'll have to use this. So this is the Hubble Space Telescope spectrum. The spectrum covered by Hubble Space Telescope.
I move this table towards the side so it will be easy for you.
Is it moving?
Yeah. Put a piece of paper also.
No, we don't need the paper. This will be fine. Yeah, that's good. Yeah, but I don't want to cover that thing. Okay. Yeah. So no, that's okay. It's okay now. In the black, it is working fine. Yeah, it's working fine now. It's okay. Yeah. Whose is this? Oh, yours. Thank you. Yeah. So if you see the range of a spectrum, electromagnetic spectrum covered by Hubble Space Telescope is from in this range, instead of going through the numbers, just very narrow range. Whereas James Webb can cover a whole lot more. So if your spectrum or lines you are seeing are because Doppler shifted or cosmological redshift is very high, then they will be shifted. See, the lines which are emitted here might be shifted in here. So it can measure far in that range and can go to very high redshift, whereas Hubble Space Telescope has limitations, much more limited in that. Now, one of the things I tried to understand was the smaller galaxies appear to be more massive than larger ones, which is quite the opposite of the common view. So I reviewed one of the paper, which is by Lovyagin, a Russian author, in late 2022. And what he found that thank you. What he found that the angular size measured, if they measure the angular size of a typical galaxy, assuming it to be 10 kiloparsec in size, suppose it is 10 kiloparsec in size, what would appear to be the angular size in different redshift? So he considered this was their authors, he and his colleagues, considered various data which is available previous to the redshifted data from, or the James Webb data, and this is the previous black one, and this is the red one, or the James Webb data. They find that James Webb data is really saying that perhaps the standard model, which is lambda CDM model, is not giving us the correct size of the galaxies. Essentially, the sizes were appear to be, if the sizes were 10 kilopascal, they should be much larger in angular size than they were being observed. Whereas they tried some non-expanding universe kind of model, which is one of the models is the twilight model, and I will discuss that in a moment. If we use that particular model, then they found that that fits the data very well. So we say, okay, so tired light, why not use tired light? Tired light, the problem is, and same data is produced here in a different form. I will not spend time discussing that. So what happens if tired light is so good, why don't we use that? The problem is tired light doesn't fit so many other data which are produced. Like the most important data in that is the so-called standard candle data provided by the supernova type 1a. It is like a standard candle. At different distances, you can observe what its brightness is. From that brightness, you can try to determine what they call the luminosity distance, and from that you can define a distance modulus parameter, and with the redshift here. And you see this data, mind it, these are logarithmic scales, so this difference, which appears to be relatively small, is really huge. So what happens, it doesn't fit that data. This is the most critical observation any model has to satisfy before you even go any further. If it cannot satisfy this, then you might either give a reason why it doesn't satisfy, or you just throw the model in the bin, dustbin. So what happens, tired light, or what is tired light? It's briefly, photons energy loss is proportional to the photon energy itself and the distance traveled. Okay, that's the tired light. So farther it travels, more photon lose energy, and for losing energy means they are becoming redder, redshifted. So that's what is happening in distance travel and photon energy. The tired light conflicts with the CMB observation. Cosmic microwave background, another thing, why it's so uniform all around it. If it is tired light says it is coming from various galaxies, then how can it be so uniform as we observe? So that uniformity and some other things I can't go in detail today, and they show they conflict with the cosmic micro background uniformity of that observation all around it. It cannot satisfy the supernova data which I have plotted here. It fails the Tolman surface brightness test. This surface brightness should evolve differently in an expanding universe and a steady state universe. It cannot satisfy that. And then what is the cause of the tired light? Okay, another one fails the time dilation test. And cause of the tired light, what is it? People thought it is a Compton scattering, but Compton scattering will cause the blurring of the object, and it is not observed. So then this was rejected. But we don't know what is causing the tired light, but a lot of things we see in physics, we don't know what their cause is. The cause is what we are counting you people to find what the cause is. For example, in nuclear physics, when I started studying nuclear physics, people didn't know about quarks. We thought how the particles are made. We later knew that they are from quarks and all those. So, there are a lot of things we don't know. It doesn't mean they don't exist. We can't explain what is there. So essentially, cause of tired light we don't know at this moment. Now, if you consider, why not we then consider a hybrid model? Expansion models is, let's say, the standard model is expansion model that explains a lot of things, but perhaps not so well the James Webb, some of the James Webb observation. So if we blend the two models, can it explain things better? So that will be what you would want to consider first. So what we did, we consider the lambda CDM model, which is the standard model, and then we say, okay, let's blend it with the tired light model and see what happens. So this is the standard model, and this is the model which includes retired light. It still does not fit this data. Most of the data here, it doesn't fit. So that model is not really good enough. Then we said, are there other models we can consider? I have been working with a model which is called the covariant coupling constants. Now, Dirac in 1937 proposed, after observing that universe might be expanding, he proposed, or he hypothesized, I should say, the gravitational constant is perhaps evolutionary. It is evolving with time, decreasing with time. Also, the fine structure constant perhaps is decreasing with time, but we are more concerned about the gravitational constant. What we did, we modified it to allow all the constants of nature to vary, evolve with time in an interrelated way. An interrelated way comes from that all the things in the universe are interrelated. And we considered an exploding star, for example. Exploding star involves multiple energies, like nuclear energy, the gravitational energy, your thermal energy, you have radiation energy, all these. And when you apply local energy conservation laws, you cannot allow only one constant to vary. As soon as you vary one constant, you have to allow other constants to vary as well in an interrelated way. And that's what we call the covariant coupling constant model. If one constant varies, others also vary. So we say, let's try the covariant coupling constant model with the tired light and see what it does. And what we found.
So you mentioned here that as universe expands, the time dimension varies in this particular model.
No, not time dimension.
Sorry,
it is the space dimension.
But why not the time dimension?
Time dimension is related to space dimension through speed of light. So if space dimension varies, then time dimension will vary accordingly in that one interrelated way. See, this is what I have seen. This is what I was saying in the last one, but I don't have time to go in detail with that, except to point out that how they are related. If f is a dimensionless function, so how speed of light, g0, h is the Planck constant, k is the Boltzmann constant, gravitational constant, how their variation is related. So if what you see when you try to measure a variation of a constant, you can't measure. If you keep c to be fixed, that means you are fixing f. If you are fixing f, you are automatically fixing g. So you cannot determine the variation of one constant by constraining other. But most of the all the experiments which have been done, or observation, they have been done to determine the variation of this constant, or keeping one other constant. Why? We don't know how they vary. So let's try to keep other constant and try to determine variation of one constant first, and then try to think of anything else. But you can't. Also, interestingly, how they are related, if you see dimensionally, what is the length dimension of each of these, then you will find if the length dimension itself varies, or the unit of, you might say, dimensionality unit or length unit itself evolves as ft, then you will find the same relation as we get here. So when we take that kind of thing and we plot on this supernova test, acid test for any model, we find that lambda CDM model, CCC model, CCC plus TL, and lambda CDM plus TL model, they all fit this data well. So they all are good for this range of observation. So we see, let's try to see whether they are good for other observations. Of course, they are not good for James Webb observation, we know. So when we try that, lambda CDM, put on the James Webb observation. It doesn't fit. CCC model on its own is useless. Lambda CDM plus tiredlight is useless, as we had done before. CCC plus TL and the tiredlight itself, they are really pretty good, considering that this graph is really assuming all the galaxies have the same size, but they don't have same size, so there is why their scatter is there. But there is a hope that this is pretty good. They're not like these ones.
But in this fitting, you get a particular covariance matrix.
Yeah,
values,
yeah.
Which is the same for the previous fit as well as for this.
There's a difference with that, but I mean, these are going into details. You are right, but that is because at this point we are not looking into more details of this. We are looking superficially. Yeah, broad. Yeah. Now, how the ages are related, I'm not going to in detail. The details are on these plots, but I don't think I have time to really discuss, except saying that here is the redshift, and here is age in one model, and here is the age in CCC plus tiredlight model. This is the well-accepted model. This is the model we have seen, and see how the age is 26.7 billion years at present time in our model, whereas 13.8 in 13.7 or 13.8 in the lambda CDM model. But if you go in the past at high Z, you have a lot more difference. It's almost, this one is almost like multiplied by a factor of 12 or something. It's a factor 5.37 when it is almost or about 400. 14, 4.8, this one 300. So you have more than 10 times advantage in space, or here you go, it's more than 20 times advantage at higher Z in forming the galaxies. So you have more time to form the galaxies if you go in this model. That means we don't have the problem why such massive galaxies exist in the universe and so on. Sorry? This is the redshift here.
And this reads,
Sorry?
green strip.
Green strip shows the giga years. This means billion years of the age corresponding to these redshifts. That's right. And this one is in the standard model age, and this is corresponding to each of these. If you just draw that, that's for the new model.
So this also means that James Webb is not looking that far back in time.
No, but depending on which model you are assuming, they are thinking according
to the last model.
last model. Yes, they are not looking that far in the back in there. Right. So they have not reached that thing. Similarly, the size. How does the size evolve? Size evolve. You can see at z equal to 10, we have size about 10 times that compared to the standard lambda CDM model, whereas in other models it's not so much advantage. Similarly, now you might see what is the fraction of tiredlight redshift compared to the expanding universe. That's we have shown in here. That one is about 20%, 22% in both the models, CCC plus TL and lambda CDM plus TL model. But as you go to higher redshift, say 1000, this really goes down to only about 3.3%, this is 3.5%. So this ratio is not determined arbitrarily. We say so much is tiredlight, so much is the expansion. It is determined by the equations, which I will just in a minute show what these equations are. See, this is the basic equation. I'm just going to very in a basic form. The expansion of the universe is squared. Essentially, you might say here, what is that? Okay. All right. This one is essentially determined by the densities, various densities in the universe. Matter density, which may be matter, standard matter plus dark matter plus radiation, and if it is dark energy, then it is Without putting dark energy, this equation doesn't fit the data. Okay, so that's why dark energy had to be brought in by after Hubble observation. In the CCC model, we don't have to add density. We have that parameter alpha, which defines the dimensionless function, how the various constants evolve. We put h plus alpha squared instead of h squared is then related to the matter density and the radiation density. And this matter density turns out to be so small that it can only account for the standard matter we know about. There is no question of dark matter required here. Just let me go and show you. And these are the various equations which I'm not going to go there. Say skip this slide. What I want to mention, it shows how standard model equations are modified in the CCC plus TL model. This is the metric. These are the equation evolving Einstein equation, Friedman equation, and all that, how they are modified. I don't have time really to go through in detail, and perhaps most of you will not be very interested. They are, but I just am showing it to see there is a strong mathematics behind it. This is also a condensation of the real mathematics. And this is another slide from that. In what I'm showing, the distance traveled by light calculated by two models, expanding universe models of covariant coupling constant. This has this form, and this is the twilight form, but distance traveled is the same. Just like if you are driving a car, you have friction of the road and the drag of the air. The distance covered is the same, but both are making you use the fuel in the car. They are all contributing to the petrol which is being used in the car or in your vehicle. So,
the size of the universe is the same in
sorry?
that indicates that the size of the universe estimated earlier and based on this model are the same.
Actually, the thing is that this is a steady state in the case of the tired light. So size is unlimited in that. Whereas size and age is only limited here, size and age is not limited in the tired light model, but it becomes limited because you have, this is the distance travel defined in the expanding universe, and light is getting tired in expanding universe, so it is constrained by the parameters of this. But because the distances are the same travel, and you can, in the limit of very small z, they should be the same, and from that we can find what is the relationship between that. So I just want to show this slide to see there is a very good mathematics behind it, not arbitrarily we are not determining those parameters. Yes? It's because of the fan I can. How alpha is defined? Okay, alpha, let's see, where is that alpha? Here, this alpha you are saying. This alpha is not finely structured constant. Its alpha is defined by fitting the supernova data. Supernova data is the acid test data. So you might say, why we are taking this function? Why not take any other power law function or something? So if we are taking this function, because we find this function does not have singularity if alpha is negative, and the alpha turns out to be negative by fitting data, and it is easy to handle in our equation.
So that means when we compare these two models, we can deny the effect of dark energy, right? This model. So what if this alpha is something relation?
Exactly, and I'm coming to that in a second.
So this is a first order differential equation kind of solution, right?
Yeah.
The variation of time.
Yeah, this you mean, is this a first order difference? Yeah, this is only single parameter. It can be more complex. It could be you can have 2 or 3 or 4 terms in there, but that makes it more, you want to make a model as simple as possible to satisfy Occam's razor. But you can always modify. Even lambda CDM model, people are trying to modify by defining how the dark energy might evolve rather than being constant, how the dark matter and dark energy might be interacting, and they might be changing the physics. So they're more complex, or a lot of what you call emerging galaxy or gravitation energy models, how the gravity itself could evolve with time. Gravity, scalar tensor theory, so many other things are coming, but they're making things more and more complicated, and they are only able to explain part of the whole problem. You want a model which can still be applied to a lot of problems you are trying to solve. Let me see what time is. Okay, so this one I have handled. Now, the results which come out, the results which are coming out here, if you see, are H0. This is the Hubble constant, which says the total expansion rate of the universe, which could be what, or you might say how redshift is related to the distance, you might say. How that is related, that is the total one, but really the component which is caused by the expansion of the universe is given here. For this starlight, these hybrid models, they are about the same. These parameters for all the models comes out to be about the same, so that is very good. Then the tide light component is also not very different for where the tide light is involved in here. Now, if you consider their goodness or fit parameter, which is the chi-square, they are not very different either. Number of free parameters are about the same, but what is different is the so-called deceleration parameter, or rate at which the expansion of the universe is happening. That happens to be significantly different. The age of the universe in two models which are not including tide light is approximately the same, 13.8, 13.7. But when you include this thing, then even in the tide light, the model doesn't fit, lambda CDM plus TL, the age of the universe is significantly higher compared to the standard model. In this one is even higher, which is the CCC plus TL model. And that one comes out from the model. So what is so big deal about it? But media made a big deal about it. I didn't make a deal. I thought it was just an ordinary paper, but media found that was very interesting. The age of the universe is twice. So this is only a number, Why should we care about it? Yes, the care has to be done. Now we found out more analysis we did, and we found, yes, when the age is, this is only twice. This one and this one only twice. But if you see the early time, the age difference is 10 times, 20 times or more. That's where the galaxies are forming. That's where we got the big advantage. Okay, if you see the energy density in the standard model, which is given here, what is this? Okay. Okay. Why is it flashing? And the top one to be used?
One is used to. This one is used.
Oh, I see. Okay, so you see the lambda CDM model has this 73% dark energy, dark matter 23%, and the standard matter, which is also divided into the luminous matter, which you can see in the sky, and the matter which you cannot see. So most of this, only 10% is the luminous matter. Most of it is non-luminous standard matter, and the dark matter is defined differently. So when you consider that, and we find out how much, and here the numbers given, if we say how much is the total matter, total energy density in the CCC plus starlight model, it turns out to be not more than the standard matter. So all that energy density, this critical energy density is 0.25, 10 to the power minus 27. It is hardly enough to really be equal to the standard model. So there is no dark matter or dark energy. Dark sector is absent in this model. But now let's try to consider, again, skip this slide, but since you are asking me this question, what happens? What happens? This is the equation we are using, but you can have this alpha term taken on the right side. And then you can rewrite this equation, and then you will find that these things can be related to the dark matter and dark energy in a way. But this is phantom dark matter or dark energy. They are not real ones. What is causing them? Because the forces of nature are weakening with time. And that weakening of time, weakening of forces of nature is giving you the effect of dark matter and dark energy. They are not real dark matter and dark energy, which we are showing here. Not only that, the ratio of dark matter and dark energy, so-called, is evolving in our model, if you can call it a dark matter. But I don't have time to really go through in detail, just to show you it is important. And when you apply such weakening of the forces of nature, can also be accounted for the astrophysical observation. We were talking about cosmological observation. Astrophysical observation, if you apply that, then that can also be attributed to this dark matter, which is galaxy rotation curves, gravitational lensing from galaxies, velocity dispersion in galaxy clusters. All these things and more can be accounted for by this weakening of the forces of covariant coupling constants effect.
Do these forces go asymptotically to zero as time progresses?
They are going in the form of function I gave you to zero, yeah, which is, I think I had shown earlier. No, in one of the slides, let me see, that might be,
The form of the equation sort of says that.
yeah, that's right, that's one, not here. Actually, it might, I had shown in one of the slides, here, this is the form they have. Okay, at z equal to 25, these things are get flattening out, and this is 1. This is 1 here, not 0. And then, of course, they are going to keep going down, down, down. Eventually, they will become 0. You are right. Okay. Yeah, we were here. Right. So now here I'm showing just the galaxy rotation curves. What we do, what we observe is what is the speed of what is the rotational speed of various bodies like star or gases or something at different distances from the galactic center. So this is what we observe. Then what they find, okay, we have so much matter, means the luminous matter, and so much of the matter which may be the gas or something. So we combine all that, and they find the plot curve like this for the standard matter, baryonic matter. But we can calculate from our model, using just this information, which is observation of the rotation curve, we can calculate what is the baryonic matter which should exist. So that is the green line here, dashed line. And this is very close to that. Of course, that requires certain turn-off density requirement, which is given here, which we require some kind of parameters to really fit, but that parameter is fairly standard. They're about the same for all the galaxies, but we are using very simple approximation. If you use the proper shape of the galaxies, then you can avoid having that fudge factor in there. You can eliminate that thing. But we are just trying to see that astrophysically it is consistent. So this is, the model is the only to our knowledge which is cosmologically and astrophysically consistent. You don't need to bring another model to explain the galaxy rotation curve or gravitational lensing or dispersion velocities in clusters. Now this thing is the CMB, cosmic microwave background. In very crude way, I could say the oscillations in hot primordial baryon, which is a standard model, is standard matter, photon fluids result in cosmic microwave background and isotropy when it cools to form atoms. And these perturbations gives rise to the sound waves which propagate in fluids, and angular size of the sound horizon, which is the primary anisotropy, which is corresponding to these things which are propagating. That anisotropy is measured by Planck center light to be, this is the angular size. Now this angular size is then converted, is model dependent, which converted into the physical size of that. Our physical size comes out to be a whole lot more, but when we are fitting, we have to depend on what we measure, not what other models are giving. So what we say, okay, that's the size. We took the baryon density, standard matter density, to be 100% of the matter density in our model, and then we slightly adjusted this alpha parameter in the function, because after all, that function is not cast in stone. That could be any function. But we had used a very simple function, that slightly varies, but we keep the Hubble constant the same, unchanged, and we are able to fit this. We get this kind of angular size giving this result. There is no room for dark matter in this, in our cosmology. Another thing on that is the structure. These perturbations which are in the, or disturbances which are really in the cosmic microwave background, whatever gave rise to cosmic microwave background, anisotropy, that also result in the formation of the structures, large-scale structure in galaxies. So what they did the 2-point correlation function of the separation of millions of galaxies at 0.2 Z to 0.7, and they found there's a little peak in there that shows there's some accumulation of galaxies, you might say, at certain distribution. And when we calculate this peak, we get the same value as in the lambda CDM model. So this is consistent too. Then we might ask the galaxy formation. How does this affect the galaxy formation without the dark matter? We don't have dark matter, so should affect the galaxy formation. So galaxy formation itself will be affected because of absence of dark matter, and not considering that we have phantom dark matter in our model as well. So that has to be kept in mind, that there is a dark matter, but ignoring that there, we can see the free fall time of matter to form the galaxies or stars would be higher. That will be higher. Similarly, the cooling time, because unless the molecules, atoms cool, they cannot really keep becoming, the galaxy cannot start to form without the cooling of this. So that is also takes longer time. But then the time you consider total time advantage, which is a whole lot more. So see, at z equal to 100, it is 46. So when take at z equal to 100, this thing, we find we still have 2.6%, 2.6 times advantage in forming the galaxy in the new model. And it will be a lot more when we consider that we do have that phantom dark matter due to the weakening of the forces. So, you know, and if you see what happens then in the standard model, these are the limitations. And this is from Cosmic Dawn Center from Denmark. They had this curve that as you go to higher and higher redshift, the mass which can be accumulated in the formed galaxy decreases. This decreases as redshift goes. And green is the region prediction from lambda CDM model. And this region can be extended if the galaxy formation is more efficient in early times than at present time. And this pink region, that is definitely out. That cannot happen. But what we predict that the galaxy formation starts at much higher Z than predicted by the standard model. This one is about the age of the universe. One of the criteria of the age of the universe is stars cannot be older than the age of the universe. So whenever people found the stars are older from any model, they thought there's something wrong in their stellar model. So they adjusted their stellar model to make sure they are compliant with the age of the universe, which was accepted at that time. But this paper, the author of this paper was going to throw this paper in the bin, or a dustbin, but they saw my published paper and they could dare to say these things, that age of some of the stars in globular clusters, very old stars, is 19 to 20 billion years. So it is less than the age of the universe here, but more than the age of the Lambda Citium universe. And similarly, I wouldn't say there's something called the time dilation effect. In an expanding universe, it takes longer time for photon to reach us, and expansion is happening. So if there's a shape of the light curve or at the emission time, that shape of the light curve will change as it is received. It will not be the same shape, which is essentially due to the stretching of the time, you might say, or aging effect, you might say. And that aging effect, if you see, it has been determined in so much uncertainty in their determination that the only line you can exclude is this one, which is the tired light. But if you see the hybrid model is the C plus TL, and Lambda Citium this, you cannot exclude one. Unless you improve their sensitivity, you cannot say that hybrid model is not feasible or not consistent. Now you might say, how can we not measure its variation? Do I have a few minutes? I will just finish in a few minutes. Sorry, it is taking longer than I expected. So what we do, gravitational variation, that was because Paul Dirac really predicted that. So for that reason, people measured, a lot of measurement have been done on the variation of this constant, while lunar laser ranging, solar system radar data, binary pulsars, all those things. But what is involved in here, the Keplerian orbital period is defined by this. Now, if this period is not varying, they say G is not varying. But if you consider R here, this R varies as f to the power cube, that function we defined, and G varies as f to the power cube, so really their variation cancel. So you won't be able to measure it by these methods. Similarly, there are other, like this is another method, measuring the constant variation or speed of light by gravitational lensing of quasar. The quasar gravitationally lensed by a lensing galaxy, and it will have different images having different paths, and different paths, longer paths will have longer time, which could be about 2 months or more, difference in this time and that, and you might be able to say, oh yeah, so we should be able to measure the difference in the speed of light because it's changing. But really, if you see the formula for the geometrical time difference in Shapiro delay, they all are G over C cube, and G scales as F cube, and C 0, this is F cube, so there is really, this is not varying. You will not be able to detect it. Similarly, in gravitational waves, G over C cube is involved. So you will not be able to see it. Similarly, say, okay, we have Oklo nuclear reactor, for example, right here. Very old reactor, and we should be able to find the variation of the fine structure constant. But fine structure constant in our model, fine structure constant is dimensionless, so it does not vary. Anyway, it could vary because of some other physics, but not the physics we are talking about. So, challenges. Can one design an experiment that can unequivocally confirm or falsify the predicted variation of the coupling constant? That is measure F, not the variation of a particular constant. And with this accuracy, and make sure that the measuring tool itself is not changing with time. It will also change with time. Similarly, design an experiment that can demonstrate the twilight phenomena. Since this path length and this experiment we just talked are different, you might say twilight will have higher shift in here component than in this. But that shift is so small difference that we don't have the sensitivity of the equipment even in the foreseeable future to be able to detect it. But if you can come up with something else, that will be great. So I want to just, towards the end, this is my last slide in a way, or last one, but one major media concern. A lot of articles were written after I published this paper, and major media concern was there are more fit parameters than in the lambda CDM. But you saw we have two parameters, and they also have two. So people assume if we are using another tired light, combining it must be additional parameters. Time dilation observed in supernova not included. We have included time dilation. Tired light adds blurring effect to distant galaxies. We do not suggest its scattering to be the causes of tired light. It does not present CMB black body spectrum. CCE, I did not discuss in detail, but really this is a very important thing. But we have, and published in the paper in APJL, Astrophysical Journal, that CCC plus TL preserves the black body spectrum. Constant variation not detected, constant variation cancelled. Individual constant variation not per CCC. Dark matter in astrophysics not explained. It explains galaxy rotation curves and galaxy cluster, as I briefly mentioned. Universe age inconsistent with globular cluster stellar age. Not so if stellar modeling is not constrained. So that is about it. In summary, what we did, CCC plus TL model, we resolved the impossible early galaxy problem, consistent with CMB first peak and baryonic acoustic oscillation data and the low Z data, they are consistent. The yield baryon or the standard matter density about the same as the lambda CDM model. That means without requiring dark matter, is compliant with the galaxy rotation curves, not in conflict with globular cluster ages, and constant variation prediction not in conflict with the observation. Galaxy begins at high redshift. So our immediate problem which we are working with, we consider only a part of CMB, but really we have to consider the full cosmic microwave power spectrum fit, which we are working. I have a postdoc who is really working on that, and we have a specialist sitting here next to you, sir, madam, who knows about it more than most of us, or all of us perhaps, including me. I don't know so much about it. And BBN, Big Bang nuclear fission, primordial element abundance, we are working on that, and galaxy and large scale structure formation. These are major projects. They are not a smaller thing, but they must be done in order to prove the model is really good. And so we are right in the first step of a new model. We have to climb another 200 steps. Thank you very much for your attention.